Welcome to the Ignatius Press podcast. I'm Father Joseph Fessio, SDA of Ignatius Press. The topic for this episode is artificial intelligence. And we're very pleased to have as our guest a good friend from many years back, Ilyas Khan. He's in England. And I won't go into his long background, but what's important for this episode is that he is, several years back, maybe 10 years ago, he founded a company called Cambridge Quantum Computing, which was basically a company to produce software for quantum computers. And 3 or 4 years ago, they became the leading software company. I think I can say that, simply objectively, Ilyas, for the quantum computing software. But then a few years back, 2 or 3 years ago, they merged with Honeywell's quantum hardware computing division. At the time, Honeywell was the number one and the leading hardware producer for quantum computers, and they still are. So now we have this company called Quantinuum, which Ilyas was initially the CEO. I believe now, Ilyas, you're the product development head. Is that it?
Correct.
Okay. And so we're going to talk about Augustine Institute, AI, artificial intelligence, about what it is, how it works, what are its benefits, what are its dangers, is it really intelligence? But I want to begin in a little unorthodox way, Ilyas, because I want our listeners and viewers to know that because Ilyas is a good friend and he started this company for quantum computing, I get interested myself. He became my mentor. And so he gave me various books I should read on quantum mechanics and then on quantum computing. And so I've delved into that fairly deeply with him as my guide. And I want to just lay the foundation for what we're going to say about artificial intelligence, or AI as it's called, because there's a basis here which can be forgotten, but it's very important. AI is done on computers. You can't do it on an abacus. You can't do it on Post-it notes. You have to have a computer. And right now they're using classical computers, not quantum computers. But what does that mean? What is the computer that's the basis for this artificial intelligence? Well, basically, it's a device that we human beings create it to manipulate or process information. And so you put in information, but you have to put it in a language that the machine will understand or can manipulate. It stores that. You put in some instructions. It processes it. It stores the result and displays the result. And what's the language that it uses? Well, it's a mathematical language, and it's got a physical basis. Basically, on a basic computer, you got transistors. What are transistors? They're little things that can hold a charge. What's a charge? A charge is electrons. So you can either hold a charge or you can discharge it and have no charge. And we conventionally say, okay, we're going to call a charged transistor 1 and an uncharged transistor 0. And so let's just say, take something very simple. You want to go 2 + 2 = 4. You have a computer with a keypad on it. You hit the button which says 2 on it. The computer does not know what a 2 is. It can't read that 2, but that's translated into zeros and ones. It happens to be 1, 0. That'd be 10 in the decimal system. It happens to be 2 in the binary system. Okay. Then you hit another button which says plus on it. Well, we know what that is, a plus sign. What does a computer know about that? Well, you translate that in a language it can understand, like 00111, whatever it might be. You hit the 2 button again, it puts another 1, 0, stores it somewhere. And then you hit the equals button. Again, that's some zeros and ones. And what does a computer do? The computer now operates on the 2 pieces of data, the 2 and the 2, the 1, 0, the 1, 0, and it does the addition and produces 1, 0, 0, which is 4 in binary numbers. And then it displays it on a screen so that we can read. the number 4 with a certain font. But that's what it's doing. Now, they're very stupid. They can only count to 1, but they're very fast, and they can count millions and billions and trillions of times. So that is what a computer is doing, and there's a physical basis. What's the physical basis? The basis is these transistors, which have charges of electrons. So electrons are the basis. And I just want to, I'm going to stop pretty soon, Ilyas, let you talk, but just one further step. I hope we get into quantum computing and how quantum computing is going to be merged with or hybridized with classical computing for artificial intelligence. But what we have, the little transistor that holds the 0, 1 is called a bit, and it's either 0, 1. And you have 2 bits, they're not connected at all. 0, you had 1, 0. But qubits, quantum bits, are amazing because they also have a physical basis. It might be an electron. Electron could be spin up or spin down. That could be 0, 1. But with a qubit, here's the magic. An electron is both up and down at the same time until you measure it. So a qubit now has twice as much information. That's called superposition. But there's a second element that whereas bits are independent of each other, autonomous, you can make qubits so that they're connected, entangled, it's called, so that this is an up and a down, this is an up and a down, but if you measure that one and it's up, that one's going to be down. And you can multiply these qubits and have them interconnect, and that's what gives quantum computing this incredible power that classical computing just doesn't have. So we'll get into that a little later. So that's the base. I just want to make it clear that AI is done on a machine that's made by human beings, and every machine is superhuman. That is, a hammer is an instrument. No human being can drive a nail with his hand. You have to have a hammer. A calculator is superhuman. I can do 2 + 2 is 4, but I can't do cube roots of 12-digit numbers. So every machine we make does things better, faster, and sometimes which cannot be done by human beings. But that doesn't mean it's not a machine. Okay, I've spoken way too long. Ilyas, let's start off. Tell us, what is artificial intelligence? How does it work?
Well, Father, first of all, thank you for having me on this podcast. And thank you also for the introduction, because I think it is important for us to understand that we're talking about an object, a machine, a computer. And that computer is something which has to be programmed or manipulated and created by a human being. I think that's really important for everybody to understand from the start. The idea of artificial intelligence is commonly taken back to Alan Turing. And Alan Turing is commonly referred to as the father of compute, I think rightly so. And Alan Turing is often misquoted. In a paper in the early 1950s, Alan Turing talked about something which we today refer to as a Turing test. And the most common view of artificial intelligence is that a machine, a computer, will not only be able to do things which humans cannot, and you articulated that very well, but also we as human beings, when we interact with that machine, won't be able to tell whether it is a human being that we're interacting with or another machine. And just to make that point more emphatic, you use the example of a calculator and a hammer. We could talk about aeroplanes and cars as well. There's no question that we cannot fly, but an aeroplane can fly and we can fly in it, but we never mistake an aeroplane for a human being. The idea of artificial intelligence becomes intriguing when not only do machines can machines do things that we cannot or that we find very difficult? But when in our interaction with them, we start to think of them, the machines, as being human-like. Over the last few years, and I would say particularly 2 years, a change in the power and the flexibility of hardware in computers, particularly something called a GPU, has allowed programmers to utilize the vast amounts of data that currently exist. In fact, the entirety of human discovery in a educational sense, discovery that can be written down in the form of plays and songs and computer programs and mathematical papers. All of this information is now available. And whereas you and I, Father, would struggle to read a small fraction of it, never mind understand it, machines can access that information and can respond to questions that we ask of it.
And so that's a first step in artificial intelligence, I understand, is called pre-training. You've got to have the input. You scour the internet and you get all the images or all the audio or especially all the words, all the texts, and you have that. But when you said, talking about Turing, you said that he's often misquoted or misunderstood. What's the misunderstanding exactly?
Well, I was coming on to that, Father. So you've established that everything is a machine and everything is physical, and you need a machine, and the machine can be a tool. We've established that computers can do things better than human beings can in certain areas. And we've established that the power of existing computers allows those machines to access information which might represent the totality of human learning over the time that we have been human beings. Now, coming specifically to the point about artificial intelligence, it's very interesting that at different times over the last 70 or 80 years, that phrase artificial intelligence has meant different things. There was a time very recently when IBM created a computer that beat for the first time in 1997 a human being at the game of chess. And that represented at the time artificial intelligence, a machine, meaning that it was artificial and not a human being, and then doing something intelligent, meaning playing chess. When Alan Turing wrote his famous paper, he actually starts the paper by saying that any question that is asked of me, Alan Turing, which says, what is artificial intelligence, is a nonsensical question. The idea that we can define intelligence is nonsensical. The artificiality of it, therefore, becomes a second order nonsense. These are my words, not his. So he actually poo-poos the idea that we can talk about artificial intelligence. 99% of people that I've ever met who reference Alan Turing and the Turing test and his paper omit that critical point. Alan Turing in his paper is explaining how one might contrive some machine to fool a human being and think or make the human being think that it is human. But he himself says this whole idea of intelligence is not something I can address. I don't have the words to address it.
All right.
This is hardly ever referred to. I'll make one more point, Father. And then I think, hopefully answer the question. So if we think about where we are today, artificial intelligence is referred to as a system that is human-like and which can answer questions that we ask of it in a human language. And the question could be anything from, could you write me a history of the Ignatius Press? Or it could be, I'm writing a paper, and in this paper, here are the questions that relate to calculus. Please give me the correct answers. So it could be anything where we interact with the machine using a human interface.
All right, let me see if I can describe in simplistic terms what I think may be happening, and you can correct me or expand on this. But let's take ChatGPT as an example. That's mainly text-based. You ask questions, it gives you answers in text, usually English language if we're doing it here. But so to start with, you mentioned the hardware that gives the possibility of having all this information gathered. I mean, they go to the internet and they scour it, they scrape it, and they get 200 billion words, let's say. And, you know, we're used to billions and trillions with our national debt, but just so you keep in mind that 1 billion, if you counted every second, you know, it would take over 30 years to get to 1 billion. And if you got $1,000 a second, it would take you 30 years to get a trillion. Or another image would be if you had dollar bills, $1 billion would be 60 miles high. That's how much a billion is, an immense number. We can't really imagine it, so we have to use these different kind of analogies to try and get a grasp of it. Okay, so they get all these, but what do they do? Computers don't understand words. They just have numbers. So what do? They give every word a number. There's 50,000 words in the English language, but they don't just do words. They do what they call tokens. So you might take ing as a token and un as a token, as in undo something. And so there's about, I think ChatGPT has about 200,000 tokens. I think that's what it is. So what they do is, let's say the word hello is 2 numbers in the computer, and they want to find out what's the next most likely word to come after hello. And so they scour all these billions of tokens, and they find all the hellos in there. And then there's 200,000 possible words that follow hello. And they give you, well, this number comes up 1% of the time, and this number comes up 10% of the time. And so statistically, the computer determines by mathematical calculation that certain words are more statistically likely to come after the word hello. And then that makes their second word. They make the most likely word. And then they take those 2 words, hello world, let's say. What comes after that? Well, most likely it's a period. But in any event, the first stage of AI is to gather all these words, translate them into numbers, and then whenever you want to make a sentence, take the first word and see what's the most likely word after that. Take the 2 words, most likely after that. And so it's all statistical. So I think you could say that in that sense, ChatGPT is a simulator of the internet. It can reproduce things, but as you said also, Ilyas, none of those words, well, they all eventually go back to human being. The internet is full of words that start with human beings. Even AI-generated words go back to human words. So either directly or indirectly, everything in the internet comes from a human being. But so that's how I understand the first stage of AI. It's pattern recognition. It's statistically creating sentences in English that we can find elsewhere on the internet because of the statistical probability of the third word coming after the second, fourth after the third, and so on. So, Ilyas, you want to correct that or add to that, or is that correct? What I'm saying?
Yes, Father, it is correct. I think that the history of compute from the very earliest days, from the 1950s onwards, is the history of applying more powerful machines to statistical analysis and using, they refer to them as stochastics, but it's the same thing, as you've said. The likelihood of the next word or the next move or the next direction. And in the 50s and the 60s and the 70s, all the way through to now, it is the same process. What has changed, however, is that the types of things which we're now encountering and the ways in which we manage them, if you remember, Father, in the 70s, even interacting with a computer required a PhD. You started the podcast by reminding us that a computer doesn't understand words. We have to program it in order for it to respond to things that are natural language. And I do think that there is something here which is quite remarkable, which is that the interaction that we have with ChatGPT, with Claude, with Gemini, with DeepSeek, this interaction is now getting to the point where it is seamless. I could be sitting in an armchair and I could speak to a speaker and I could say to the speaker, I'm hungry. Please order me some fish and chips. And instead of saying it to my friend, my brother, my carer, my spouse, I'm saying it to a machine. And within the same period of time, the fish and chips would appear. Now, the point, and here I'm very much in the camp of a computer scientist called Yann LeCun. And Yann is the chief AI scientist at Meta. Maybe that's not quite his right title, but he's a very distinguished AI scientist, one of the godfathers of AI. And I think that all of these points which make ChatGPT very powerful are simply still reducible to a probability, which in turn highlights their limitations. So whilst it's good for us to be impressed by what's happening, we should also realize that there's no causality. You know, Father, how a young child learns language and how we understand, for example, the contextual background to my conversation with you, it all happens in a very tiny part of our brain. And that is, it's very easy to think that that is mechanical. It's very easy to think, oh, we can reproduce that. But these large AI systems, these large language models, are not reproducing what is going on in our brain. In fact, far from it.
Well, you mentioned large language models. That LLM comes up as an acronym. Can you describe what a large language model is for us?
I think you've already done a very good job of that, Father, but I'll have a slightly different go of it, and I'll keep this very short. Less than 10 years ago, within the realms of computer science, we discovered and created something called a transformer. A transformer is, think of it as a widget. So it takes the hardware and enables a hardware through some clever manipulating of first order logic. So first order logic is what determines the foundations, for example, of mathematics. If this, then that. You very neatly talked about zeros and ones, Father. As you know, that is referred to as the excluded middle. We are forced into one or the other of an answer. So the manipulation of first order logic and the clever use of this new power in these parallel processing units allowed people to come up with a transformer. And a transformer is what led to our ability to build neural networks and for those neural networks to be let loose on information, which is a sum of all human knowledge, the internet plus many, 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 many other sources. A large language model takes as the base of its knowledge all of the information that, for example, might exist on the internet, and to log that information and give it an address. Right? Think of it as everybody in San Francisco who has a home having a unique address. The large language model then is powerful enough because previously we did not have such powerful machines. The GPU unleashed this power. It's a bit like, Father, in the old days, having an aeroplane but not having a spaceship. You know, we used to have airplanes. We could go from New York to LA, but we couldn't go from Florida to the moon. And now we can with these new engines. So GPUs are an engine. Using that engine, we can now do things that we couldn't. And the large language model allows us to do exactly what you said, which is ask questions and mitigate the fact that we'll get a random answer by using these things called vectors, which measure distance and measure also direction, and give us some semblance of a formal response. So a combination of the GPU, the transformer, and lots of data give us these language models that are quote unquote human-like.
That's very helpful. Now, you mentioned neural networks. Let me take another stab at this because it's named after neurons, which we have on our brains. My understanding, Ilyas, is that you have layers of nodes in a computer, and you might have, thousands of these nodes on one layer, but each node is connected to all the other nodes on the next layer. But you can determine how much influence each node has on each of those, what's called a weight. So this node is connected to that one. We put 100% weight on that one. This is connected to that one, 40%. This one, 0%. And so you got all these nodes in a layer connected to all the other nodes in the next layer, and there's several layers, and you can tweak the weight of the influence each node has on each other node below it. So now you have these nodes with information that goes through them, and you have a question up on top, what is 2 times 2? And it goes through all these nodes, and at the bottom it says 6. You say, well, that's not right. Let's tweak it. Let's change those weights, Now it's 5. Well, that's not good enough either. So you tweak the weights. By the way, there's millions of these things, or hundreds of thousands anyway. So it's a human being couldn't do it in a lifetime, and therefore you have this computing power that is able to do it with billions of cycles per second and all these different addresses that you talk about. So anyway, a neural network is just that, nodes, layers of nodes that are connected in ways that you can adjust the...
I would nudge you, Father, I would nudge our audience and you away from that just for a second.
Okay.
And let me tell you why. So first of all, you're absolutely right that the reference point and the use of the word neural is taken from the neuron. So that much I think is clear. But actually, I prefer to think of this as a graph.
As a what?
Graph, Graph.
Okay.
With
Oh, you mean graph? Graph. I got it.
and bear with me. We'll come back to why I think of it more as a graph.
Okay.
When you came up on this machine that you and I are talking on now, I immediately recognized you, and I knew it was Father Fessio. And it happened instantaneously. And when I look at a dog, or I hear the sound of my wife, or so many different ways in which I could give examples, even 2 and 2 equals 4, my brain acts in ways which maybe are similar, but only at a very shallow level for the neural networks that exist in computer science. In fact, we do things very, very efficiently. You know, it takes us a few hours to learn how to drive a car. Pretty soon we do it without thinking about it. We're not constantly processing information. And the attempt, and I think this is very important, I think the attempt to equate a neural network with a human brain is a very shallow thing, that it's really only similar at a very superficial
Okay.
level. That's point number one. Now coming back to why I think I'd like people to think of this as a graph or a graph rather than lots of. The reason is that you have all these variables. So you have supervised learning and unsupervised learning, and you have recurrent neural networks and all these different types. And really, all they are is fancy words for talking about intervention. I'll give you a perfect example of what I mean. If the system that we're interacting with knows us, it can make decisions that are better because it knows us well. The best example is Amazon. I've been using Amazon a very long time. There's not really any neural network involved or artificial intelligence involved. We used to be very impressed when it remembered what we bought and what we purchased and made some recommendations. Or you bought Hans Urs von Balthasar book called Prayer. We think that you'd be very interested in another Hans Urs von Balthasar book. So that is actually in principle no different. And we didn't used to call it artificial intelligence in those days. The idea that it gets to know us, the system gets to know us, and therefore can respond, is almost similar, Father, to this reorientation of weights. And I think the difference between LLMs and what we used to think of as these neural networks is that in the case of an LLM, the system is refined based on what it knows about the question that's being asked. So it is generative. It's not just repeating what's already there. It is generating something that is new. And I'll give you an example of where this can be dangerous. Do you remember recently, I think it was Google, were criticized because their AI system was meant to be too, should we say, traditional, and it wasn't reflecting the diversity of the world. And so somebody then said, well, give me a picture or an image of German soldiers. And suddenly you had a Negro or a black person wearing a Nazi uniform. And this was the system hallucinating because it had been told to be diverse and represent the world. So for the same reason it can be powerful, these large language models can also go haywire.
Yes, you use the word hallucinate. That's a term of art, I believe, in AI. That yes, they can produce human-like sentences. It's got a subject and a verb and a predicate and so on. But then they can, like you say, make a black Nazi soldier or something like that. The sentence might be perfect, or even the image might be, a real image, but it's not of a real thing. Okay, so that's you would prefer to talk about graphs rather than neural networks. Ilyas, I get the impression that you don't think artificial intelligence is truly intelligence. It's not. There's some kind of qualitative difference between it and human intelligence. Am I correct on that?
Yes, Father, you are. I think we're now at the point where we need to be responsible and we need to stop going down the easy route of aligning ourselves with somehow a message that these are human or human-like systems. That's where I have a bigger issue. I'm very impressed, as we should be, by the advances made in LLMs and code LLMs. I think you and I have talked about this before. I'm excited by the application of science for scientific discovery in medicines and genomics. But the idea that somehow these systems are humans or could replace humans or be human-like is very fanciful and in fact quite dangerous.
All right. let's talk about some of the possible uses of AI and possible benefits. I would say for one thing, it is a more comprehensive search engine. If you want to search for something and you have a long question, it's pretty good at scouring the internet and coming up with the answer you want of factual things. And I would say, comment on this. You can take the whole internet as your data for a AI, program. But let's say I'm interested in medical technology, and so I scan every single article ever written in every journal, every scientific journal about medicine, about pharmaceuticals, and so on. Then I can ask questions, and instead of my having to go to the library and try and read all those, which I couldn't, the AI can sort through that and kind of give me a summary of who said what. So I find that as a potential beneficial use of AI, focused data, where you can actually take this large, but it's still limited, and you can extract things that you are interested in. Is that what other uses would you see?
So, Father, I think this is where we start getting into the area of subjectivity. I have to agree with you that it's an extremely useful tool. And whether it's the example you gave of knowledge being gained, or, for example, looking at ways in which we can become more efficient in something fundamental like protein binding or peptide binding, I should say, in the case of biology, that allows us to think about molecular structures which could aid our good health, which is a very important use case. I think this is undeniably a positive. Where you're right when you sense my caution, and my caution is not in that area. My caution is, first of all, the vast amount of resource in the form of money and in the form of energy and other resources, which are being poured into something with a false expectation. And the false expectation is that somehow around the corner, we have this thing called AGI, artificial general intelligence, which is the wording, the phraseology that people use in order to say this is indistinguishable from a human. Father, you asked me about the most important application. Let me answer that.
Okay.
Yeah. So, Father, I think that actually the most exciting thing about large language models for me is not what they can do now, or even what they might do in the future. It is how, in conjunction with quantum computers, we can create or accelerate applications in the area of biology. And when I talk about biology, our biological systems are the most complex systems that we as humans know. In fact, we have more success in looking up at the universe and learning about space and planets and galaxies than we do about understanding our brain, or how this mystery of DNA works and how it mutates and how we carry these genes for generations. So my excitement is that I think within a very short period of time, meaning less than 5 years, a combination of a powerful quantum computer with powerful large language models that are capable of doing investigative work that human beings would find difficult, as you mentioned in the case of some experiment that you're writing a paper about. I think a combination of those two things, looking at how we might tackle disease at the cause and not the symptom, and how we therefore could give dignity to people who are currently at the end of their life, or that have these illnesses which are impossible to deal with, the oncologies and senility and other diseases of that nature. So, Father, I think that is really important. And I actually think that that doesn't get enough airtime. And we end up talking about all this, what I think of as rather trivial exercises of large language models, such as, doing replies to letters for lawyers that otherwise other lawyers would be writing. I don't doubt that that is interesting economically in some cases, but actually we should be looking at discovery, scientific discovery, because all of the advances, Father, that we can chart for humanity from the start of the dawn of time are linked to scientific discovery.
Well, let's dive a bit deeper into that. So, first, to exclude something, looks to me like you're not concerned that AI or AGI, general intelligence, will somehow become so superhuman it will take over the world and be making decisions and extinguish us or whatever. That's science fiction, and there's no basis in science for it. But quantum computing is something you are deeply, deeply involved in. And my favorite physicist of all time, not Albert Einstein or Ernest Mach, or it's Richard Feynman, was a great physicist at the end of the 20th century. And I believe he said that if we want to investigate nature in its deepest and most fundamental, dimensions, we have to use quantum mechanics, quantum computing, because quantum is how nature works. And so I think that's part of a reason why you're excited that quantum computers will do things that classical computers simply can't do, no matter how much power they've got. But here's an example. Proteins, all these molecules and so on, all these atoms, but they fold, and the same protein can fold different ways and do different things, right? But how do you predict the folding? But do you think that quantum computers, because they are mimicking in a certain sense the underlying physics of reality, will be able to do experiments, and predict folding or something like that, so that they can produce outcomes, like you say, that will actually cure something from the cause and not from just a symptom?
Yes.
Or maybe I should ask it differently. I mean,
No, I do. Father, so my view on this occasion is really important. When we do have a view, if it's subjective, then we need to say so. So quantum computers are going to be the most effective when we're simulating a quantum system, and problems related to the simulation of a quantum system are exactly those that Feynman spoke about. And it's why people are so excited about quantum computing, and we're talking about new drugs, we're talking about new materials, etc. It is at the moment uncertain how exactly a quantum computer could be of benefit in, for example, protein folding, other than through the application of informatics. So data analysis. We've just published a paper on knot theory, which you will love reading. As of the date of this interview, it's just come out. It'll be in your inbox soon, Father. You'll find it, and you and I can talk about that separately. What I'm really interested in, however, is not the aspect of informatics, such as, the statistical nature of this or that happening because of the way protein folds or other things mutate, from the point of view of looking at DNA as a starting point all the way through to the genes. I'm actually thinking of first principles. And this is not proven, and I don't want to suggest that this is something that will happen for sure. But the more I've looked at this in the last few years, the more I'm convinced of the Schrodinger approach, which is that there is something fundamentally at the base level that determines how our DNA works, which is quantum mechanical. And I'm more interested in looking at unlocking that avenue rather than looking at all the statistics that we have and trying to determine what happens next. That is valuable, but that's not what excites me. I'm looking at first principles.
Interesting. Okay. Let's see if anything else.
That book, Father, is What is Life by Erwin Schrödinger. And it is, in my opinion, very relevant to where we are today. It may be that my intuition is incorrect, but that's what I referred to before when I said I get excited.
All right. Let's see. I think we've covered most of the things I wanted to cover. Is anything else that we've left out that's important, Ilyas? We should.
Not really, Father. You might want to ask me when do I think quantum computers will have a societal impact? Because they've mostly been in the lab. How far away are we? You might want to ask that.
All right. Well, let me ask that question, Ilyas. When do you think we'll actually have something practical come out of these computers? By the way, last time I looked, they can do factoring, which is how you break keys. But the largest number they could factor was 21, I think. I don't know.
We're beyond that now. We're
okay.
Yeah. No, I think that the practical impact of quantum computers will be in the next 2, maximum 3 years, and it will not be a quantum computer on its own. It will be a quantum computer working in tandem with a large high performance or supercomputer. And my view is that the area of topological data analysis is the area in which there will be early impact. And this is way earlier than many people imagine. 2 or 3 years, Father, is a blink of an eye.
That I have a question related to that, because we now know that the energy requirements for using classical computers for AI are enormous. I mean, billions of megawatts they need, and they're going to build nuclear reactors to create the electricity they need. Oh. Well, when they make these hybrids, will quantum computers, do you think, have lower energy requirements to
in fractions of what's required? Think of quantum computers as being, think of classical LLMs being good at big data and possibly, maybe big problems, but typically big data, whereas a quantum computer is looking at solving big problems with small data. But the complexity of that small data, small molecules, for example, quantum mechanical interactions, the complexity of that small data is such that it requires the Feynman approach, the compute as nature computes, rather than this contrived classical computer.
Thank you, Ilyas. And because you are in charge of this product development, which is what's going to make it happen faster, I want to thank you for the time you've taken. We've delayed the coming of these practical consequences by an hour now, but I want you to get back to work so we can see them soon. Thank you, and God bless you, Ilyas.
God bless you. Thank you, Father. Pray for us.